We are almost done. A little bit left to talk about. Am I wrong, by the way, that that particular chapter feels a little bit less dense? It's a little bit less of a journey to get through, you know? And then I think because generally speaking, there's less calculus. There's vector cross products and the flux integral and the wave equation in the previous chapter, and we get to this one and things feel, it's almost like, oh, this is downright comfortable compared to that. Is it just me? Appreciate that. I'm asking because it's a lot to talk about all in one night. We're discussing like 2.5 chapters worth of material, which is a lot, but it's kind of okay, compared to some of the other chapters, which took us like 2 full nights to talk about. I feel like I didn't really rush that last chapter. Not really. I mean, maybe a little fast, but we took the time to prove Snell's law. So it is a lot. And if you're starting to feel like, oh, Jesus, a whole nother chapter. I get it. I don't actually want to cover the whole chapter necessarily of geometric optics. Something going on outside that door. some scrabbling from the dog. I'm not sure. My favorite part about the Young and Friedman text, anyway, in this particular chapter, is the fact that it derives the equations that we might be familiar with. I mentioned that earlier. The reflected rays reflected by a plane specular surface appear to our eye to have originated from a point behind the mirror. If we follow these lines backwards, why can't I draw? If we follow those lines backwards, our eye does the extrapolation and says, oh, they all came from over here. And that's where the image appears to be. We say that is the image because it is the apparent source of the rays that we observe. It isn't the actual source. The actual source is over here, but that's okay. It appears like there is a thing. What's the difference? Why can't I do both? Hold on, let me. This worked a second ago. There. Image formation by a plane mirror. We can consider a couple different test rays Here's one that is normal to the boundary and that reflects normal. That one looks like it comes from this direction. Here's another one that isn't normal, reflects so that the angle of incidence is equal to the angle of reflection. Looks like it came from this way, so the image is here, and we can derive the relationship. The image is equally far away from the object as, or I'm sorry, is equally far away from the mirror as the object is away from the mirror. We say that the image is virtual. If I lived behind the mirror, I couldn't put a, there's no bright spot that I can focus onto a piece of paper. There's nothing actually there. It only looks like it's there. It's only the apparent location. It's not an actual location. There's no focusing. There's no spot here, no bright spot that I could actually like shine onto my hand. It's not there. It only looks like it's there. For a mirror, which we expect to reflect, because the image appears on the other side of the mirror where the light isn't, we say that it is on the wrong side, the non-reflection side of the mirror. And we use a negative distance to talk about the fact that it is behind the mirror, not where we expected to find the light. So S prime in this case is by definition negative, so that if we want to equate the distances, we have to use an additional minus sign. S prime is by definition negative, so the negative of the negative quantity is the positive object distance, S. Virtual, it is vertically oriented the same, but horizontally reversed. And it is the same size. We could define magnification as the ratio between the image size to the object size. For a plane mirror, the magnification is 1. As you know, the right hand in an actual right hand, the object makes an image of a left hand. So we have a handedness, a left-right orientation reversed, but up and down are still the same. The object exists at point P. The image of that object follows the law of reflection. A ray that leaves the point object at P along the optical axis hits the mirror and reflects back the other way. That's perpendicular incidence. A ray that hits at some other point here obeys the law of reflection, so those two angles are equal, and passes through. The two rays intersect at point P prime. Here we see S and S prime, both of which are positive because the image is on the reflection side of the mirror where we expected the light to be. So we use the positive convention. Both S and S prime are positive. If I advance to the next slide, do we get a derivation of this relationship? No. No. Okay. Let's talk about the angles first. There's a little bit of a trick from old school high school geometry. We know that angle alpha is the sum of the opposite two interior angles. Okay. So that means phi here, if we ask for the opposite two, so it's not this one, but alpha and theta. But if we do the same trick, beta is phi plus theta. So if we eliminate theta from this system, we end up with that. All right, how does that help? Let me erase some of these markings here because they're kind of getting in my way. We need distance h. We need that. And we also need distance delta. The tangent of alpha is h over opposite over s minus delta. The tangent of phi now, phi is the angle drawn between one radius and another. so that the tangent is h over r minus delta. Because the distance between point C and that spot is r, we just have to subtract delta again. Oops. And last but not least, tangent beta is h over s prime minus delta. If these angles are small, then tangent of an angle is about equal to the angle itself. And if we feed these three relationships into this one, we end up with that. I'll let the ins and outs be a curiosity for you. R here is the radius of curvature of the spherical mirror. If the center of curvature is on the same side of the mirror as the object, let's let R be positive, just like when the image is on the same side of the mirror. If everything's on the same side of the mirror, it's positive. If the center of curvature happens to be on the other side of the mirror, let's use a negative value for R. Why? Why is this true? Each time we draw a normal at the point of incidence. Now, this is normal to a circular mirror, well, a spherical mirror, but a circular mirror. Each time we draw the normal to a circle is a radius. In order for this angle to equal this angle, we can, again, geometrically show that this distance needs to be half the other distance. The point at which a spherical mirror focuses parallel plane light, PLANE, the point at which it does that is the focal length, and it is half the half the radius of curvature. So if we put that together with the equation that we had a second ago, R is twice the focal length. So well, yeah. We have a slightly different version If we are told about the radius of curvature, we can use the version that's in the red box. If we are told about the focal length of the mirror, then we can use that slightly different version. Where again, if we're talking about the concave side, the focal length is positive. If we are looking at it as a convex, bubbling out towards us as opposed to bubbling in away from us, then we have to call it a negative focal length because the focal point is on the wrong side of the mirror, the not reflection side of the mirror. Let's draw two test rays from the furthest point of extent of an extended object. I'm not a huge fan of, I like the second one. A ray drawn through the center of curvature is going to be traveling along a radius and is going to be perpendicular incidence. So it will reflect back this way and pass back through this way. This other one is hard to draw. I need a protractor in order to make sure that angle theta is equal to angle theta. The easier test ray is the one that is parallel to the optical axis, like these are parallel to the optical axis. A ray coming parallel to the optical axis strikes and passes through the focal point. But the focal point is half the radius of curvature. So we're someplace here, I suppose. It's measurable without a protractor, which is what I like about it. And the reflected ray passes from that point through the focal point and extends away from there. And we do, in fact, get the same intersection point of the two rays I'm considering. And that is the image of the point of furthest extent of the extended object. So we can extrapolate and draw the image, which is upside down, inverted, let's say. The magnification is, for this scenario, smaller than 1. The size of the image is smaller than the object. And this, though, is a real image. If this were a flashlight, I could focus that light on my hand at point P prime. There is actually light that focuses there, as opposed to the light behind a plane mirror. Well, which there isn't. The image behind a plane mirror, the light actually isn't there. Here, the light is actually passing through this point. Here again, yes, I suppose with a protractor, we could draw these two rays with the angle of incidence and the angle of reflection both being theta. It's hard to do. Instead, I would consider the focal point on the other side, draw the ray parallel to the optical axis. Missing that ruler from the notepad. And then the reflected ray bounces off. Bounces off so that the extrapolation passes through the focal point. This image is virtual. No light actually reaches this point, P prime or Q prime. The image is upright, erect, and it is smaller than the object. Yeah. The corresponding image distance for this situation is negative, it says, because it's an image that is virtual and is located, the point of intersection, the apparent point of intersection of these rays is behind the mirror. So we use a negative distance, which means if S prime is negative, so is R, and so is F. And yeah, their first choice, ray number one, is the ray that is parallel to the optical axis that reflects through the focal point. Choice number two is the ray, and there's you have some freedom with these, a ray through the focal point reflects parallel to the optical axis. That's the vice versa. A ray through the center of curvature is reflected back upon itself. Those are the three that are kind of go-tos. If we really need a fourth, the pink ray that is drawn here will get the job done. I don't expect to need a fourth. Same stuff for the other shape of a spherical mirror, if the object is on the other side. It's just that the image is always virtual because it's on the wrong side of the mirror. If we're talking about refraction, though, now we have to consider that we are moving from one medium to another. We could use an identical geometrical derivation to show this. Plane refracting surface behaves like Snell's law, but the angles are related to the apparent sizes of images. This is a special application, I suppose, or maybe Snell's law is a generalization of this, or some vice versa. Two spherical surfaces close enough together that we can ignore the distance between them. Basically, all we care about is the fact that there are two spherical surfaces. The convention for a converging lens, in other words, a ray bends towards the optical axis, tends to focus them as opposed to spread them out. A converging lens has the convention that the focal length is positive. For a lens, we expect transmission. That means we're talking about the focal length on the transmission side of the lens, not the same side of the mirror, the other side of the lens, because we expect the light to go through. The same equation applies. Because we're not really treating the material of the lens itself. We're just saying, all right, the rays propagate until they get to the line that represents the center of the lens, and then they bend according to what you told me was the focal length. So the geometry is exactly the same as that of a spherical mirror. We're going to end up with exactly the same equation. And in fact, we do. A diverging lens, on the other hand, the rays are diverted away from the optical axis, which means that if we're standing over here, they look like they came from back here on the original side of the lens. That's not where I expect them to be. That's not where I expect them to focus. I expect them on the transmission side of the lens. This is on the wrong side. So we'd represent it with a negative focal length. Note that a plano-concave, or I guess a meniscus, certainly, a meniscus could be converging, could be diverging, could have a positive focal length, could have a negative focal length. What's the difference? Well, any lens that is thicker at its center than its edges is converging. Any lens that is thinner at its center than at its edges is diverging. This is the thing. I don't think this was ever, I'm trying to recall if this was ever derived for me when I went through physics classes. I think it was just told to me. I want to come back to this. Graphical methods like ray tracing, we can call it, is very similar for a lens as for a mirror. The rest of the chapter discusses the application of these initial principles of the behavior of mirrors and lenses to devices. Now, all right, now that we know how light propagates and we can predict what it's going to do when we put stuff in its way, mirrors and lenses, what can we do with that? This is a survey of applications that is better suited to your investigation than my presentation? The fact that I need prescription lenses at all, and I guess I shouldn't. The reason I kept those sunglasses for so many years is that they are prescription sunglasses, um, considerably more expensive at the time than just a regular pair of sunglasses. So they were prescription polarized, and like I didn't know when I was going to get another pair. I was a starving grad student at the time, and I needed to keep what I had. But I need corrective lenses, glasses, because I am nearsighted. So this is particularly relevant for me. Magnifying glass is just a special application, useful, a special application of a converging lens. We can stack lenses in sequence. And if we do that in the right way, we can get very different applications. That was a really quick survey of the applications. There's more in the textbooks that you're working from. Before we leave this unit, I'd like to look a little bit closer at the lens maker's equation. Okay, so let's dig in. We got 10 minutes left. Let's consider a meniscus type lens. Maybe plano convex, whatever. And we have an object here, a distance S1 from the lens. Don't want to put it there. S1. There are two spherical surfaces here, each of which has a refractive job to do. The result, the image that would result from the refraction of the first one, becomes like an intermediate image, an intermediate object. And we can treat it like that's the thing that we can use as the object for the second spherical surface. And that refracts that, the first image, and we end up with a final image when we're done. So we're going to use the image formed by one surface as the object for the second one. Now, these surfaces, the outer, the one closest to the object, is curved more than the other one. So these centers of curvature, the radius of the first surface we encounter is shorter. Not by a lot, but yeah. This isn't to scale. I'm not going to get the curvature right. I mean, it's maybe here or so. We'll call that the curvature of the first surface. And some point further back is the curvature of the second. Because the curvature of the second surface is shallower, which means it has a larger radius. All right. If we use the thin lens equation that we got from geometry in terms of the fact that this is a, wait, no, not a thin lens. This, we're talking about first, this is a reflection, that refraction at a spherical surface. So we need the version of the equation that has to do with the indices of refraction. Okay. So we're talking about the index of refraction in medium A and the index of refraction in the material of the lens. If we use the spherical refractive surface equation that we had in the slides, I'm just going to look it up to be sure that I'm getting the right one. N of the first medium over the object distance, N of the second medium over the image distance is the difference in indices, second minus first, over the radius of curvature. Okay, hold on. What did I just say? the index in the first medium over the object distance S1 plus the index in the second medium over the image distance S1 prime, I suppose, equals the difference NB minus NA over the radius of curvature for the first surface C1. Well, no, wait a minute. C is the center of curvature, the point at the center. That's a point. We want the distance R1. Now, if we do that, there will be an image formed by that first refractive surface. And if we follow the outline of the picture that we saw, it'll be, I don't know, somewhere where? The point suppose the image is formed here. We're treating it as if only the first surface matters. Pretend like the second surface isn't even there. Okay. So following the derivation on that one slide, we're imagining a triangle that looks something like this. And that's the image point of the point on the optical axis. And we can extend from there and show that this is going to be the image. But that's the intermediate image, which we're going to use as an object for the second surface. So we need this distance. And then if we use this like spherical surface refraction again, to get out of the wait a minute. Our image is over here, and we're propagating into the spherical surface again. So NA is the air, and we are S1 prime away from the lens, and B in the lens gets us to S1 double prime. I don't think I need 1. I think I just need S if I'm doing the prime thing. That cleans things up a little bit. Wait a minute. there's a polarity issue here. There should be a minus sign because we're on the wrong side of the lens to begin with. With respect to the actual physical lens, the intermediate image is on the wrong side. It's on the transmission side, not the object side. I'm starting to think we need that. Uh-oh. But we are, as we come across from the object towards the lens, we go from A to B, and there is some refraction. And now we're here in medium B, and we're about to go back to medium A. I think I've got to reverse these. Okay. I know we're already out of time, but we are close to done with this. Suppose that the outer medium is air, such that n sub A is close to 1. Then we can just call this little n. N sub A is 1. That's just n. And the numerator there is just n minus 1. N sub B is just n. N sub A is 1. And this is 1 minus n. What if we add these two equations? And what if we treat the lens as if its thickness is irrelevant? So we don't really need to measure from one surface or from the other surface. We can just kind of measure from the lens, from where it is. So I think well, let's see what we get. Oh, interesting. Because if we add these two equations, those two terms are going to cancel. We can reverse the subtraction, and then we can factor out n minus 1. For the other, like if we pretend for a lens on its own if we're going to treat it like there's an optical, like a center line, and we're just going to treat it like a thin lens like we were before, we've got the same equation as we had for a mirror. 1 over s, 1 over s prime is 1 over f. But all together, we've got an object and a final image. That's this. So that means the focal length of the effective combination of the two lenses and that's the Lensmaker equation. Appreciate the extra minutes. Appreciate your attention today. Have a great weekend, everybody.